see in the cover image, a simple image, animated GIF, shows you slip along strike-slip fault. So if you look at the surface, this whole surface here, you have a little piece of fault scarp exposed after displacement. Now this surface is the fault plane itself, and it's vertical, you can see. So this vertical plane is the fault plane. And if you, again, imagine dipping this plane into full of water, a tank full of water, then any horizontal line contained by this plane, which is basically here, this edge of the cube, is strike line. And look at the motion along the fault plane. So as this block shifts to the left relative with respect to this other block, all the motion vectors point out the direction in the horizontal slip or displacement in the horizontal plane to the left. So this motion slip to the left on this block, or right directed displacement on the other block, is what we call slip or displacement along the fault plane. So strike-slip faults, these are special type of faults where the displacement vector is parallel to the strike of the fault, like I explained. Because of that, we can also say strike-slip faults will have silicon lines parallel to the surface of the Earth. So silicon lines will be horizontal on the fault surface. I will show you some examples shortly in the next slide, the next couple slides. So silicon lines will be horizontal. If you remember normal fault structure, silicon lines, which are scratch marks left on the surface of the fault plane as other fault block moves up or down, right? So those scratch marks left by other mobile block are silicon lines. In this case, they will be horizontal. In dip slip faults, silicon lines will be in the direction of dip. If they are perfectly perpendicular to the strike of the fault plane, in this case, they will be perfectly parallel to the direction of dip, because dip direction and the strike are always perpendicular. That's the relationship for planes. But for silicon lines on strike-slip faults, in this case, they will be parallel to the strike, they will be horizontal. So when you measure rake, which is angle between any two other structures, it will be, in most cases, 0 or very close to 0. Okay. I'll show you some other examples as we move to other slides. Strike-slip shear zones. Shear zone and fault. These are two different things in terms of deformation mechanisms. Strike-slip faults, or in general, faults are brittle structures. The deformation mechanism of a brittle deformation. So everything will be fragile in colder temperatures. So deformation will be irreversible, permanent breakage of chemical bonds, right? For other case, brittle versus ductile deformation, we already compared these two in the previous lectures. In ductile deformation, the type of deformation is more like molten plastic. So material can flow under really great amount of stress, or if temperatures are high enough, material will be weakened and softer and will again flow under stress. So this type of deformation will form strike-slip shear zones, and materials will not be broken like a brittle fault plane. In layers will be still connected, but you will see displacement or offset along the layer without losing cohesion. So these strike-slip shear zones form at much greater depths, and they are dominated by plastic deformation mechanisms. Typically, strike-slip faults are steeper than other types of fault planes. In extensional settings, when you find normal faults, they can have a range of dip angles. They can be almost horizontal, maybe even horizontal, from with 0-degree dip angle to 90-degree dip angle, which is vertical. So those dip slip faults can be anything between 0 to 90 degrees. But mostly what we see in real world examples, those high angle normal faults are usually up to like 60, maybe barely 70 degrees. They still have pure dip slip component. After 60 or 70-degree dip angle, for some reason, maybe it's becoming too steep to the surface of the earth. Most of those faults, what I have observed in the field, they have a strike slip component on top of normal sense of slip. So it's a combination of normal or reverse plus strike slip component, which makes them oblique faults. So as fault planes become steeper and steeper in the real world examples, they become strike slip faults. These type of faults can occur on all scales and lengths. They can be tens or hundreds of kilometers or miles long, like San Andreas Fault example in the West Coast. The San Andreas Fault is at least 100-mile long structure cross-cutting the entire West Coast, almost entire West Coast. And they can be some of the longest faults in the world, if you check examples other than San Andreas. So there are two types of possible motion along strike slip faults because, like we said, the formation or slip will occur parallel to this strike line, which is right here, this line. So these two blocks will move relatively, right? So one block will shift to the right, another block will shift to the left. So they will pass each other. In this case, how can you determine sense of slip? Basically, you imagine you're standing on one of the blocks and observe the other block. Whichever direction this observed block moves relative to where you are standing, that gives you a sense of slip or structural tectonics. So in this example, if you stand here on this block, the other block is moving to the right, so it is right lateral or dextral strike slip fault. And the second example, if you stand here on this block, other block moves to the left, so it's a left lateral or sinistral strike slip fault. It will be the same sense of slip if you move to the other block and observe the other one. Still, you will find same sense of slip for each case. So in this block diagram, we have all three types of faults together depicted very good. That's why I wanted to show you all three together so you can see how they are different, how normal faults, reverse faults, and structural faults are different in terms of slip direction or mechanism. So here on the left side of the block diagram, we have a normal fault. As you can see, it's a dipping plane. It is not vertical, it is not horizontal. It's a very steeply dipping fault plane. So slip along this fault plane occurs in the direction of dip. What's dip direction? Again, a reminder, dip direction, if you pour some water on the surface of this plane, whichever direction that water flows, that's the dip direction. So in this case, if you add directions on this block diagram this way, let's make this way west, this side of the block diagram east. So this plane basically is dipping to the west, and this slip along the fault plane also occurs in that direction. So this block is sliding down relative to footwall, and these two blocks are basically spreading out in this direction to the west as a result of extensional forces, stresses. So this down dropping motion makes it a normal fault. And here we have a reverse fault. Why we call this reverse fault? Because you can see the block above tilted or dipping fault plane is moving upward against gravity. So this is a reverse fault, and you can see this hanging wall block will be uplifted for reverse tectonics.